So here we go, brand new chapter, finally. It's been a long time, been a couple weeks. We're starting gases. You may know about suction cups. Hopefully you know that a suction cup is a thing, that it exists. They are not sticky, but they stick. How do they stick? How do suction cups work?
They create a vacuum.
Sort of. It's not exactly that they create a vacuum, but you're onto the right idea. Technically, they don't create a vacuum, but I think you've got the right idea. Yeah, so suction cups and some stickers and other things will just stick on to glass. And the way that suction cups in particular are held on is by pressure. So when you stick a suction cup onto a surface, there's usually a little bit of a cavity, a little bit of a bend to the suction cup that you push down and then air gets pushed out. That sort of creates a little bit of a vacuum, you could think of it. But what's actually holding it onto the wall is that you're removing particles from inside this suction cup area. So looking at this diagram, this suction cup stuck on like a roof, for example. And everywhere else, there's gas particles, lots and lots of gas particles floating around that we can't see, we can't feel. And that's what creates pressure, is lots and lots of tiny, tiny collisions by gas molecules that are happening all the time over an area. So gas particles constantly colliding with just one side of this suction cup pushes it onto the surface that it's stuck onto. However, if you don't have a nice tight seal all the way around your suction cup, then air can creep in underneath it and start pushing on the other side, and that's why it comes off so easily. So usually there's a little tab on a suction cup. You just pull the little tab and that opens a path for the air to come through, and then suddenly it pulls off like it's not sticky, because it isn't, right? So that's how suction cups work. And if you have just a 2-inch diameter, so 2 inches across diameter of suction cup, that's held on by a force of almost 50 pounds, just from the air pushing on it unequally, just from the one side, pushing it into the glass, pushing it into the wall, whatever the material is. That's also why suction cups don't work on like stone that's not like cut to a really nice smooth polish. You usually put them onto glass, because glass has a nice smooth surface. There's no cracks for the air to get behind the suction cup. So the main idea that we want to focus on here is that pressure is a force. It's a lot of little tiny collisions by gas molecules adding up to make a big force. You could think of it like little tiny punches or little tiny, BBs or something hitting the surface, and together all of those forces add up to make a much bigger force. We don't feel pressure because we're experiencing it all the time from all sides. So pressure plays a role in the theory that we are going to use to talk about gases, the kinetic molecular theory. The idea behind the kinetic molecular theory is that we've got the kinetic part, movement, molecular, molecules, a theory explaining how things work. So basically we're explaining gases with the idea that molecules are moving around and how they move around, certain factors about the way that they move around. Catching up on my attendance real quick. So this theory is relatively simple. There's, I think, 4 or 5 points depending on which version you look at. But just like a lot of our other theories, it's not exactly perfect, so there's some caveats, some places where it doesn't work. For this class, for our class, it works well, and we're going to focus on where it works well. So the 5 points of our kinetic molecular theory. Gas consists of tiny particles, molecules often, that are in constant motion. Gas is always moving. Those gas particles have perfectly elastic collisions, meaning that when they hit something and bounce off, they don't lose any energy. So think of a bouncy ball versus like a rock. If you throw a rock at the ground, it might bounce a little bit. It's not a very elastic collision. It's losing most of its energy to the ground. If you take a bouncy ball and you throw it at the ground, it comes up, or if you just drop it, it comes up most of the way because it's retained a lot of its energy. It's redirected that energy up. So our gas particles are like little tiny bouncy balls. When they hit a surface, they bounce off. They're not losing energy. Our particles bounce perfectly. They're the ideal bouncy ball. You may have seen, if you're on the science side of TikTok or YouTube or Instagram Reels or wherever, I think Nile Red had a video about an atomic trampoline. It was like this metal surface thing, and you drop a BB on it, and it bounces for a shockingly long time, even though it's bouncing on metal. So it's kind of like that. It continues to bounce without losing any energy. And then another important point is that our gas particles are separated by large distances. There's lots and lots of empty space. So between our gas particles, this representation is not accurate to the amount of space that would be between these gas particles. There would be much, much more space between our particles relative to their size. Another important point for our kinetic molecular theory is that they don't attract or repel each other. They're not sticky, they're not repulsive. Sometimes you can get, like in the real world, you could get charged particles. And if you've got a negatively charged particle and a positively charged particle, there's going to be some magnet effects. And even in non-charged particles, there's going to be some of that. We're going to pretend like that does not exist. So if they collide, they just bounce off perfectly. There's not any sort of like stickiness to them. And then another important point, the speed of the particles, how fast they're moving, depends, at least partly, on temperature. Higher temperature equals higher speed. Colder temperature, less speed. So those are our 5 very important principles for kinetic molecular theory. It would be a good idea when we test on this for you to know these 5 points. We will talk more about where they come up throughout this lecture. Okay, so some of the properties of gases that we can observe and that fit with our kinetic molecular theory. Gases are compressible. So like if you squeeze a basketball, basketballs are full of air, you can feel the surface of the basketball give a little bit, right? It's got air that's inside of it inflating it. You can let all the air out and then it's really floppy and doesn't really work well. So you can squeeze a basketball, more similar to compressing gas here, the fun trick that many of us have probably done, or squeeze an empty water bottle, like a plastic water bottle. Do we all know what I'm talking about? Where you kind of squeeze the water bottle and then you twist it and twist it and twist it and you build up the pressure inside and then you, as quick as you can, flick the top off and then shoot it into the air or into your friend or wherever, right? That's a buildup of pressure because of us compressing that gas. So we know that we can compress gases, like squeezing a basketball, an empty water bottle, our tires. Gases also assume the shape of a container. They are not tethered by gravity in the same way that we as solids and liquids are. And so they'll fill up their container. They fill or spread throughout their container. If you've been on a road trip, you've probably experienced this. Like if somebody gets fast food, somebody's got a little snack that they open in the back, and you might be able to start smelling it up in the front. Even if the AC is not running, that's those gas particles making their way throughout the cabin. Other times it's not so pleasant smells, right, that somebody produced. And then you're, hey, let's open the windows so we can get some fresh air in here, right? That's an example of those smells filling and spreading. Or if somebody's wearing some strong perfume or cologne, right, and you're kind of in their vicinity, you'll notice it slowly start to waft over closer to you as that gas, those odors, those particles work their way over. So they're compressible, gases are compressible, and they'll also spread and fill their container. The compressible part because there's a lot of empty space, and so we can squish them together. They also, because of all of this empty space, so much empty space between the particles, they have very low densities compared to solids and liquids. A typical can of soda is about 1/3 of a liter being in the vicinity of a quart. If you took a can of soda and you expanded it out as a gas, you'd get a volume of about 2 big bathtubs worth if you expanded it out as a gas. So almost 500 liters of particles that are just contained in one soda can. If you just spread them out to be like a gas. It's a massive amount of space. Just to give you roughly the idea of how much empty space there is between the particles compared to a liquid. Pressure is also a prediction, something that we can come up with from kinetic molecular theory. So pressure is the result of the constant perfectly elastic collisions between particles in the gas, like around us, and the surfaces around them, like the desks, us, the whiteboard, the ceiling, etc. Pressure lets us do things like drink from straws. When you're sipping on a soda with a straw or a milkshake or something, you're creating a slight negative pressure in the straw, and the pressure of air pushing the liquid from the outside causes it to push the liquid up into your mouth. That's the way that you draw it up. If you've ever tried drinking out of like a water bottle with a straw, they all have a little pressure valve. They've all got a little valve in there. If you cover that and try to drink out of it, you'll suddenly find that you can't drink very much water before you have to let go, and then it sucks the water back in. So it's because of that pressure relief valve that the pressure is able to push the water up into your mouth. Otherwise, you wouldn't be able to drink from straws. It also helps us breathe. Thank goodness for that. And despite what Calvin and Hobbes might tell you, variations in Earth's atmosphere create winds. It is not actually trees. Sneezing, I think, is the Calvin and Hobbes explanation. And so changes in pressure can help us predict weather. You might have known that. There's some weather stations where like people like, oh, my knee's aching, there's a storm coming, right? For some reason, their knee is sensitive to the change in pressure. They can feel a drop in pressure, causes their knee to hurt, and they know that a storm is on the way. Pressure depends on a couple of things. We define pressure, the pressure of a gas sample, as force, like pounds. Pounds is a measure of force per unit area. So a unit of area being like a square inch. So pounds over a square inch, this is pounds per square inch, PSI. That's one that we might be familiar with. You're probably used to seeing inflating bike tires or a ball or something like that. And there's a bunch of other units for pressure as well. Pressure depends on a bunch of things. One of the things that it depends on is the number of gas particles. This is what you would experience if you're trying to fill a basketball or a car tire or something. If you've tried pumping up a car tire with a bike pump, I don't recommend it. Or if you've tried pumping up a road bike tire that go up to like 100 psi, as you're adding particles in, you've got more and more particles. There's more particles, so there's more collisions, so the pressure is higher. It gets harder and harder for you to push that bike pump to get the particles into your bike tire. So generally, if all other things are the same, more particles equals more collisions. More collisions means more pressure. And then the opposite is also true. If you remove particles, then that means fewer collisions, which means lower pressure. There are also instances of pressure imbalance that you've probably experienced if you've been up to the mountains or if you've flown on a plane. So when you drive up into the mountains, we are kind of lower, closer to the earth, lower elevation. There's more gas particles pressing down on us from up above. You've experienced this change in pressure effect, especially if you've gone swimming and you've gone down to the bottom of the pool. You can feel it a lot more acutely when you're in a pool. Swim down to the bottom and your ears start to hurt. That's because of that added weight of water that's pushing down on you. The same thing works for air. It's just less exaggerated because there's so much empty space. So if you're going up in higher elevation, you're climbing up kind of higher in the waters, this sort of analogy. So there's less pressure, there's less gas particles pushing down on you. And that results in a pressure imbalance in your ears. Inside of your ears, behind your eardrums, there's some pressure built up, and it can equilibrate with the outside environment. But when you go up in the mountains, if you don't pop your ears every now and then by yawning or chewing, or you've got the voluntary thing where you can squeeze the muscles, then you have a pressure buildup and you feel your eardrums bulge out. And when you yawn or what have you, right, you're letting that pressure out, and so you're equalizing the pressure in your ear with your outside environment. The same thing happens when you're flying on a plane. And this is often why infants and small children are crying on a plane. They don't know why their ears hurt. They just feel pain, and so they start crying. Babies will always cry on planes. And unfortunately, it's not safe to give babies gum. So you can't give them a piece of gum to chew on to help them with that ear problem, right? So next time you're on a plane and you see small children, yeah, they're going to cry. It's not their fault. It's the pressure difference that's causing them to experience that. So some of the pressure units that we'll talk about, we mentioned PSI. That's the one that we're probably most familiar with. There's a bunch of other pressure units. The easiest one, I think, is the atmosphere. The atmosphere is the pressure at sea level. Conveniently, it's the weight or the pressure, the added force of all the gas particles when you're at sea level. If you go up in elevation, the pressure drops. It's less than an atmosphere. So normally the most pressure that you'll experience is 1 atmosphere. The closer you are to sea level, the closer you are to 1 atmosphere. Another unit of pressure, this is the SI unit of pressure, so like the baseline unit for the metric system world, right, is the Pascal with the symbol PA. It's defined as 1 Newton, which is a really small unit of force, over a square meter. So a square meter, basically like 9 square feet, which is a relatively large area. So it's a small amount of force over a really large area. We won't be using pascals very much. And the difference between a pascal and an atmosphere is over 100,000 pascals. So a much, much smaller unit of force. The atmosphere one that you know is defined as pressure at sea level. Other pressure units include millimeters. Let me change colors. Millimeters, so mm, of mercury with the symbol Hg. Oftentimes there won't be a space between those, it'll just be mmHg. And this is how pressure used to be measured. So this is one way that you can measure pressure. This is not a way that you would typically measure pressure anymore because, well, it involves mercury. And mercury, we know, is not very great for you if you touch it or if you breathe it in some circumstances. The way that they would measure this is they would take a really long piece of glass tubing, dip it into a tube of mercury, a vat of mercury, flip it upside down, and then as you pull it up, eventually the outside pressure is not strong enough to push the mercury up, and you get a vacuum up at the top end of the tube. And part of the reason that they used mercury rather than water is because mercury is really dense, and so you don't need as long of a column height. It doesn't push the water up, or doesn't push the liquid up as far when it's mercury because it's so dense. If you do it with water, water's got a density of 1, mercury is like 11.5. So it's like 11 times, it would be like a 30-foot long, 32 feet long tube of glass that you would need to be able to measure pressure this way. So when you're at sea level, it pushes that column of mercury up a height of 760 millimeters. So this is like that straw effect, right? The atmospheric pressure pushing down on the mercury, forcing it up the tube. And inside the end of this tube, we've got a vacuum. There's maybe some mercury particles in there, but otherwise, there's nothing in there. And no matter how you pull this up, it's only going to rise 760 millimeters. So 760 millimeters of mercury equals 1 atmosphere. Something that I like about this explanation of millimeters of mercury is we can see that it's a unit of length. It's how high the mercury rises. And we can also express it in inches. And if you actually just convert millimeters and inches, that's the same as the conversion between millimeters mercury and inches mercury for pressure units. I think it's fun, but you'll also just have 29.92 inches mercury equals 1 atmosphere. You'll also have that given to you on an exam. Other fun pressure units are summarized here. Another good one to know, so you should know an atmosphere. 1 atmosphere at sea level, pretty easy to remember. The other one that you would want to know, arguably, is that torr is the same as millimeters of mercury. Numerically, they're exactly the same. I probably should know why they have different labels, but I don't. But they're exactly the same numbers. And if you want to save time on some of your homework problems or doing calculations, it's helpful but not necessary that you memorize these conversions. 760 millimeters of mercury is 1 atmosphere, which is the same as 760 torr. So this table might be a helpful tool to have with you. I think you also have pressure conversions on your yellow sheet. Any questions so far about pressure or our kinetic molecular theory? All right, let's do some pressure unit conversions. Please convert 1.25 atmospheres to torr and 30.15 inches mercury to millimeters mercury. I'll give you a minute or two to do that. All right, coming back after a short pause, we want to convert 1.25 atmospheres into units of torr. So we are going to find atmospheres and torr. These two units are equal to each other since we're looking at air pressure at sea level. So 1 atmosphere equals 760 torr. 1 ATM equals 760 torr. We can make a conversion factor out of that. That'll take us from 1.25 atmospheres to units of torr. We're going to want the atmospheres part of this on the bottom and the torr part up top so that our units convert correctly. So 760 torr over 1 atmosphere. The atmospheres cancel. We're left with 1.25 times 760 with units of torr. This will be 950 point, for 3 significant figures, torr. Or 9.50 times 10 to the 2, if we wanted it in scientific notation. For converting between inches mercury and millimeters mercury. We're going from inches mercury to millimeters of mercury, and we'll need our conversion factor from the table. So millimeters mercury is 760. Inches mercury is 29.92. So 760 mmHg equals 29.92 In.Hg. So starting with our 30.15 inches mercury, we divide by 29.92, putting inches mercury on the bottom, and 760 mmHg on the top. Our inches mercury cancel. We're left with 30.15 divided by 29.92 times 760. The order of those things happening isn't important, just as long as you do them all. So 30.15 times 760 divided by 29.92. It's a little over 760, 765.8, and some other stuff, mmHg. We would round this to 765.8, since the next thing is a 4. So 4 significant figures, 765.8 millimeters mercury, the same as torr. Alternatively, you could do the conversion of just the length unit, the inches and millimeters, and you'd get the same answer. How are we feeling about converting units? It's been a while, maybe. Feeling good? Do we want to do another one? I'm not sensing an overwhelming desire to do another one, so we'll go ahead and skip that. And get into more fun stuff. Okay, so we are starting now on a journey. All of us. We're going on a journey. We're going to learn a bunch of laws, but not the you can't drive 35 and a 25 sort of laws. These are gas laws. Not as exciting as Bird law, arguably, but it is law nonetheless. So Boyle's law is our first simple gas law, as I'll call them. Our firstest law, our firstest simple gas law. Boyle's law is a relationship between pressure and volume. The pressure of a gas depends in part on its volume. Pressure and volume are related. How are they related, though? That's what Boyle's law tells us. So if we hold temperature and the amount of gas constant, so like if we have a closed container, the pressure of the gas increases for a decrease in volume. We'll see a picture of that, I think, on this next slide, an application of this, rather. So this is how bike pumps work. If they're the manual pumping kind, I would guess that electric ones do the same thing. So when you're pumping up like a bike tire, for example, you may know that you have to pull up the thing like you're an old timer, like a miner about to blow up some TNT, right? You pull your thing up, and then it's filling up the cylinder of the bike pump with air. There's a little one-way valve that lets air in, so it fills up with air just at normal pressure. And then as you push down, at some point along the way pushing down, you'll start to hear or feel gas moving into the tire. And the higher the pressure is, the further you have to push it down. So what's happening when you push this handle down is you're compressing gas in this cylinder. And once you've compressed it to a certain point, it'll start to flow from the high pressure zone that you're making in the pump into the tire. And the higher the pressure gets in the tire, the further you have to push down, the higher the pressure needs to be for it to actually go through into the tire. So as volume decreases, pressure increases. This is also like if you take a water bottle or a basketball or something and you squeeze it, you're reducing the amount of space that those particles have to be. Right? You're pushing them closer together. They're going to run into each other more. There's going to be more collisions. There's going to be an increase of pressure. The further you crank down that water bottle when you're twisting it up, the higher the pressure gets inside, the harder it gets to twist it anymore, the harder that cap is going to fly off. So Boyle's law, named after Robert Boyle, Bob Boyle, relates pressure and volume. We are assuming constant temperature and a constant number of gas particles. And Boyle's law states that the volume of a gas, so volume, and pressure are inversely proportional. So this ribbon or fish-looking thing basically just means is proportional to. Why am I writing poorly? Is proportional to. And the 1 over P is also called the inverse of P, so inversely related. As one goes up, the other goes down, as opposed to directly proportional. So volume increases, pressure being on the bottom would have to decrease for these two things to stay equal. And what proportional really means is V equals some number, some unknown value, times 1 over P. So there's some constant in there. We don't know what the constant is, but it's constant. It doesn't change. And so if that doesn't change, if we increase V, then P has to decrease. If we decrease V, that causes pressure to go up. Or the way that you're more likely to remember it, P1 V1 equals P2 V2. Classic Boyle's law. Boyle's law comes from this experiment. So you can't really see it very well, but I'll mark off. There's a volume of air in these little J tubes. So from this green bit up, there's actually, that's supposed to be air. It's just silvery for some reason. And with 1 height of mercury here, there's a certain amount of volume in this tube. When you add more mercury into the tube, you get more mercury that's pushing down on the volume of that little bit of air that's in there. So as you increase the pressure, the height of the mercury, that volume decreases. This is where Boyle got his data from, or the experiment that Boyle was doing. Again, with mercury, we probably wouldn't do this in the modern era, since mercury can be bad for you. And Boyle got a graph of volume on the x-axis here with pressure on the y-axis. The math pilled among you might realize that that's an inverse function, or has the shape of an inverse function. So the way that it's written out there doesn't look very nice. But if you take it and you put 1 over pressure on your y-axis instead of just pressure, you get a nice straight line, which is good. So that shows us that we have an inverse relationship. As we increase volume on the x-axis, we're decreasing pressure. You could also represent it the other way. Kinetic molecular theory explains Boyle's law. I was talking about this earlier. If you take this container with a movable lid and you push down on this lid, you decrease the volume in this container, you still have the same number of gas molecules. They're moving at the same speed because temperature is constant. And since there's less space for them to travel, they're going to run into things more frequently. So you increase the collisions, and collisions cause pressure. So that's the microscopic why it increases pressure. Okay, we can, I know that you were all worried that we weren't going to use that formula, but we are. Here we go. So let's use Boyle's law. We'll do this one as an example. P1V1 equals P2V2. A sample of gas has an initial pressure of 2.44 atmospheres and an initial volume of 4.01 liters. Its pressure changes to 1.93 atmospheres. We are looking for the new volume. For all of the simple gas law problems, they have slightly different formulas, but the most important thing, other than doing the algebra correctly and plugging the numbers into your calculator correctly, the other most important thing is that we don't get our P1 and V1 mixed up with our P2 and V2. So there's going to be two variables that go together that are in the same set. We need those to both be either 1 or 2. It doesn't matter which one they are, you'll get the same answer. You just have to keep the things that are together. Otherwise, you will get the wrong answer. So in this problem, it tells us that our initial pressure and our initial volume are given to us. So I am going to, as I guess that you probably would, call those P1 and V1. So P1, 2.44 atmospheres. V1, 4.01 liters. And then the pressure changes. So our new pressure value, our P2, is 1.93 atmospheres. And we want to know the new volume, so that's going to be V2. So to solve the problem, we're going to arrange P1, V1 equals P2, V2, our Boyle's law, so that V2 is by itself. So to get V2 by itself, divide both sides by P2, that'll move it under P1 and V1. I'll show you what that looks like. So getting P2 moved over to the other side. And if we flip it left and right and clear out the canceled out P2, we have V2 equals P1 V1 over P2. And you'll notice that we've got a pressure on top, we've got a pressure on the bottom. Those need to have the same units. Those units will cancel out. And we also have a volume that's on the top, so that's going to be our only unit that's left over. That would be one way of checking that this is maybe set up correctly. So let's plug those numbers in. So our P1, 2.44 ATM, times our V1, 4.01 liters, over our P2, 1.93 atmospheres, and the atmospheres cancel. How are we feeling about that so far? Good, I assume. So that's what we'll plug into our calculator. So 2.44 times 4.01 divided by 1.93. Our new volume is 5.07 liters. So that would be our answer for this problem. For a lot of these problems, we can also check, like sometimes with knowledge that we ourselves know, if we did this correctly. So looking at the thing that changed. Our pressure changed, higher pressure to lower pressure. So we can think about, okay, well, what's going to cause higher pressure? What's going to cause lower pressure? If we were lowering the pressure, we'd have to be expanding, adding more volume, reducing the number of collisions. So like if we think about squeezing a basketball really hard, that's going to be our high pressure. As we let go, stop squeezing the basketball, it's got a little bit more volume, and the pressure drops. So we'd expect our volume to be higher. You don't have to go through all those checks every single time, but if it makes sense to you, it's a helpful way to possibly catch mistakes. So that's Boyle's law. We also have Charles' law, our second gas law, our second simple gas law. And this relates volume and temperature. You may know that hot air rises. You may also know that hot air balloons fly up in the sky somehow. And the reason for both of those effects is that when you heat up a gas, you're increasing the volume. You're spreading out the particles. You still have, right, particles there. You're spreading out the particles. You're increasing the volume that those particles take up without changing the density, or without changing the mass, sorry. So since you're increasing the volume, like in our D equals M over V, if you increase volume, then density decreases. So we're lowering the density of the air by heating it up. So we're basically making a low density balloon for a hot air balloon, and that causes it to get pulled up. Kind of like if you put like one of those ball pit balls that has air in it into a pool, you try to pull it down, right? It's less dense, and so it's going to float up to the top of the water. That's also what causes like the top floor of a house to tend to be warmer, because the less dense air gets pushed up to the top of the house and the cold air is going to tend to settle. So just like wood or witches float in water, or ducks, which is it? Anyway, low density air also floats in higher density air or gas. And we have a relationship between volume and temperature. So temperature, an increase in temperature causes an increase in volume if we have our temperature in Kelvin. We get a nice straight line. And this line, if we extrapolate it all the way back, when we have zero temperature, we also have zero volume. And that's where we get the idea of absolute zero from. It's the minimum temperature that we can get where nothing's moving around. And there's some debate about whether you can actually get there, but you can get really close at least. And so a negative volume is impossible, and that's why we set negative 273 Celsius or 0 Kelvin as our absolute zero point. So we're learning also an important thing here. Our temperature needs to be in Kelvin when we're working with gases. I think that's on the next slide. Hope that's on the next slide. It's not on the next slide. Just more about French mathematician and physicist, J.A.C. Charles. What a name. After whom this Charles' law is named. Temperature must be in Kelvin. Kelvin temperature. Kelvin temperature. What kind of temperature? Kelvin temperature. So volume is directly proportional to temperature. When one goes up, the other goes up. When one goes down, the other goes down. And we make this V1 over T1 equals V2 over T2. I showed on the previous, for Boyle's law, that proportional to just means equals times something. So we get to this, right, get that thing, whatever that constant is by itself, we get V over T, and that's going to be equal to some constant. If you change V or T, the other one's going to change proportionally. So you can copy paste it to get V over T on the other side. And then we're, just like cash for gold, we're cutting out the middleman. Right, so we get V1 over T1 equals V2 over T2. That's where that comes from. You don't need to know it. I explain it because I know somebody maybe thinks, oh, that's fun. So that's why I talk about it. I think it's fun. That's why I talk about it. Again, Kelvin temperature, just in case you missed that. Oh, here it is. Yeah. When the temperature of a gas sample, again in kelvins, is doubled, if we double the temperature, we double the volume. And again, that temperature needs to be expressed in kelvins. I even put an exclamation point. We're going to box that in real quick. And it's because of that line that we looked at, that graph that we looked at. We have a linear function, and if we're in Kelvin, our y-intercept, our volume, is going to be 0. So that gets rid of this plus b part of our linear function. If we're in Celsius, let's go back and look at what this would be in Celsius. If we're in Celsius, then our line goes somewhere through like this, and that's not going to be a 0 y-intercept. So then we would have to include a term for that. And we don't want to do that. I don't know what that number is. It's easier to just change your temperature to Kelvin, and then you get rid of it. Again, things you don't necessarily need to know. And the kinetic molecular theory connection is that the temperature of a gas sample, if that's increased, the gas particles move faster. Faster particles, if it's in the same volume, is going to increase pressure, but our pressure is constant, and so volume has to increase. And there's actually an experiment that you can do with this at home, which is not standing there and blowing up balloons. This was just like the only public domain picture that I could find of somebody blowing up a balloon, I think, on Wikimedia. So you got these gals blowing up balloons. So Charles' law, if you want to play around with this at home, if you've got some ice or if you've got some hot water or both, if you blow up a balloon, don't blow it up all the way, because if you increase the temperature, it's going to pop. If you blow it up all the way, it might pop. Take the balloon and pretend like it's your enemy. Dunk it into some cold water. Give it an ice plunge. And you'll notice that when it cools down, that gas is going to condense. It's going to get smaller. It slows down the particles, and your balloon is going to get smaller. And then if you pull it out and you run it under warm water or hot water, you should be able to pretty rapidly see that balloon blow up in size. Again, it could pop, so just keep that in mind. Don't surprise yourself, give anyone a heart attack, whatever. So that's something that you can pretty safely try at home. All right, I know you were thinking it. Let's do some calculations. Okay, we'll do it. Okay, so our Charles law, V1 over T1 equals V2 over T2. There's also sometimes it's convenient to have the inverse. This is the same as T1 over V1 equals T2 over V2. If you flip one of them, you have to flip the other one, but it doesn't cost you anything. You don't even have to show me that you inverted them. You just do it. It's free. This is not one of those cases where it's convenient. Okay, we've got a balloon. We fill it up to a volume of 2.20 liters at a temperature of 22 degrees Celsius, and then we heat the balloon up. Heated. New state, who dis? Heated to a temperature of 71 degrees Celsius. Find the new volume of the balloon. So just to point out our variables, we've got an initial volume, 2.20 liters. We've got a temperature that goes along with that volume. Which temperature goes with 2.20 liters? 22 degrees Celsius. Okay, and then that means that our other temperature that we're given is our T2. And we're looking for the volume that goes with that temperature. Okay, so you've got your starting point, your equation, your V1 over T1 equals V2 over T2. We've got some variables. Give it a try. Did anyone get a final volume, a new volume of 7.1 liters? Oof. You have forgotten something very important. If you got 7.1 liters, you've forgotten something very important. Something worth underlining 15, 20 times. Something worth boxing in and putting arrows at. Something worth putting in italics and adding an exclamation point and talking about it ad nauseum. You have forgotten that we need to be in Kelvin. Our temperature needs to be in Kelvin. So we're adding 273 to both of these numbers to get it to Kelvin. So 344 Kelvin for our T2 and 295 Kelvin for our T1. There's a question that I like to put on exam 3 that you need to remember to turn your temperature into Kelvin, or you'll possibly be very confused. Okay, so now that we're in units of Kelvin, we can get the correct answer. We are looking for V2. After we do our algebra rearrangement, we find that V2 is equal to V1 T2 over T1. So 2.20 liters times 344 Kelvin over 295 Kelvin. And we get a not quite as big number of 2.57 liters. We heated up our gas. When a gas heats up, it expands, its volume increases. So since we heated it up, we expect our volume to go up. We got a slightly bigger number, so that's good. That matches with what we expect. If you got a smaller number, that would be a clue. If you were thinking about what we expect, that would be a clue that something got messed up. Probably switching up your temperatures, getting them mixed up. Questions so far? This is just another Charles law problem. I'm going to skip it because I'd like to get to the combined gas law. Try to burn through some of these gas laws real quick. So Boyle's law and Charles' law can be combined. So some situations we're going to be changing two things. So this is combining Boyle and Charles, Bob and JAC. Our combined gas law is given here. And you may notice something if you think about Boyle's law, if you remember what that looked like. Right, that was Boyle's law, P1 V1 equals P2 V2. And Charles was V1 over T1 equals V2 over T2. So the combined gas law, if you like merged these two images and got the V1s and the V2s to overlap, right? That's our combined gas law. That's all we're doing there. We're literally just combine them, put them together. And what units do we need to have for our temperature? Kelvin. need to have Kelvin units. Okay, so this is, I'll call it our third simple gas law, because if you add up our first and our second, that equals 3, so that's working out real nice. All right, a little bit more of a block of text staring us down. A sample of gas has an initial signal word. We're starting at these numbers. 241 milliliters, 755 millimeters mercury, temperature 32 degrees Celsius. Those three numbers we want to keep together. That'll be our first state. You can call it your second state, it doesn't matter, just as long as they stay together. They're all 1 or they're all 2. Don't split up the values. Okay, so V1, 241 milliliters. P1, 755 millimeters mercury. T1, the goats, the world champions, 32 degrees Celsius. What should we do before we forget with our temperature? Convert it into kelvins. Let's just go ahead and do that right now. That's going to be 305 Kelvin. Then, new set of states, the gas is compressed to a volume of 115 milliliters. So our V2, 115 milliliters, and heated to a temperature, T2, of 94 degrees Celsius. Before we forget, add our 273 Kelvin. So this is 367 Kelvin. And we want to know what's the final pressure in millimeters of mercury. So we'll need to remember or look up our combined gas law. P1 V1 over T1 equals P2 V2 over T2. We are solving for P2. So we're going to multiply both sides by T2 over V2. You can do those one at a time, or you can do them together. I'm showing them together. That'll get the T and the V, both the 2's, to move from the right side to the left side, so we get P2 by itself. So P2 equals T2 over V2. Combine that line with P1 V1 over T1. Whew. A lot of variables. Questions about how we got here so far? All right, the fun part. Okay, so our T2, 367 Kelvin. Our P1, 755 millimeters mercury. Our V1, 241 milliliters. These numbers are all multiplied because they're on the top together. On the bottom, we've got our V2, 115 milliliters, and we also have our T1, which is 305 Kelvin. This is an area where it's very helpful if you write out all your units, because we can see if they're going to cancel. This problem has been set up in a way that our units do cancel out nicely. So our 367 Kelvin, these units cancel out with our 305 Kelvin on the bottom. Our 241 milliliters on top cancel out with our 115 milliliters on the bottom. the units that we end up with after we cancel those two things out, the units are millimeters of mercury. This is convenient because we've been asked for the final pressure in millimeters of mercury, so we don't have to do a conversion. You might be asked on an exam to do a problem like this, but answer in torr or in atmospheres. So you might have to add on a unit conversion. I think I don't normally do too many of those. I'll often do the unit conversions by themselves, but I do like to have a couple of questions where I combine them all. If you're putting this into your calculator, it may be helpful if you want to just use one division sign, put parentheses around the numbers on the bottom. Okay, quick as we can. All right, our number is 1,903.84 ... millimeters mercury, assuming I put it in correctly. And then we would round that to 3 significant figures. 1.90 times 10 to the 3 mmHg. If you got a much larger number, it's because you didn't use parentheses on your bottom numbers, possibly. Combined gas law questions, any? I know what you're thinking. Do we have more gas laws? Yes, we do. Added in some more gas laws just because I knew you'd want them. So Avogadro's law relates volume and moles. So this is our law 4, sort of. So simple gas law number 4, again, sort of, because the combined gas law was just 1 plus 2. So what if the amount of gas changes? Because we haven't looked at that yet. You can figure this out, measure the volume of a gas while varying the number of moles in the sample. And it turns out the volume of a gas sample, I don't know why I'm saying gas that way, increases linearly with the number of moles in the sample. This is from our old friend, Amedeo Avogadro, the guy with that number. So volume is proportional to the number of moles. So this looks pretty similar to that V1 over T1 that we were looking at previously, Charles' law. So if you want to memorize something for Avogadro's law, there it is. Or if you feel like you have to memorize something for Avogadro's law, there it is. More gas, bigger volume. Assuming that temperature and pressure are constant. Here's another picture of somebody blowing up a balloon. Avogadro's law is what happens when you blow up a balloon. When you're blowing up a balloon, you're putting air into the balloon, right? Right, however you do it. Blowing into the balloon, you're adding moles of gas to the balloon, and so the balloon gets bigger. That's all that Avogadro's law is saying. It's what happens if you blow up a balloon. And if you let the gas out, right, the balloon deflates. You're losing moles of gas, it's leaving. This is all Avogadro's law is. It's not that scary. So we've got a helium balloon. It has been filled up to a volume of 1.9 liters with that many moles of helium gas. If 0.0210 moles of additional helium is added to the balloon while the temperature is constant and the pressure is constant. What's our new volume? Before we even do the problem, before we do a calculation, do we expect our new volume to be bigger or smaller than the number we started with? Bigger, why? We're adding moles to the volume. This is like doing a couple extra puffs into a balloon that we're blowing up, right? We're adding a little bit more gas. We expect our balloon to get a little bit larger. Okay, so balloon gets bigger. That's our prediction. That's what we expect to happen. We have an initial volume. That's the 1.90 liters. We've got an initial number of moles, 0.0920 moles. He. And we also have N2. What's N2? Say it again. 0.113. Our new volume is 0.1130 moles of helium. Because the problem says, right, we have an initial amount and we're adding moles. So we're putting in 0.0210 new moles. We're adding that number of moles to the number of moles that was already in there. So that's the trick here. So this is the 0.0920 moles plus 0.0210 moles. If you use an N2 of 0.0210 moles, you will get a smaller volume, which is not what you expect. Right, so this is one place where it's helpful to be thinking about, is this the answer I expected to get based on what the problem said? Because it can help you catch some things wrong and maybe save you some points. Okay, so we are finding V2. Our Avogadro's law, V1 over N1 equals V2 over N2. So V2 is N2 times V1 over N1. So 0.1130 mole He times 1.90 liters divided by 0.0920 moles helium. The moles helium part cancels out, and we're left with liters. And our new volume, 2.33 liters, which is bigger than our 1.90 liters. So that's good. We have a consistent answer. There's also an exercise problem for Avogadro's law, if you would like to do that. And a sneak peek, what we're going to cover next week, the ideal gas law. For some of you, you don't need to memorize any of the simple gas laws, as long as you know the ideal gas law. You don't need to memorize any of them. We can make all of them from the ideal gas law. So I'll be showing you that next week.